In this video, we will be looking at two types of reactors, a conversion reaction, or a conversion reactor, and an equilibrium reactor. We'll be using a standard set of components: methane, ammonia, carbon monoxide, dioxide, etc. And we will be using the SRK fluid package, which you should now be able to configure. Previous videos, we would not have set up any reactions. We would have gone straight into the simulation environment once our component list and fluid package was specified. In this case, we are going to go into the reactions page, and we're going to add a reaction set. A reaction set allows us to group our reactions together, and what it does, it attaches those reactions to a fluid package. Therefore, the fluid package will be utilized to predict information required for the energy balances and to calculate heat of reaction, such as heat of formation and other physical and chemical properties. We're going to add a new reaction, and let's take a second to discuss the different types of reactors present. You may set up a conversion reaction, an equilibrium reaction, a heterogeneous catalysis, kinetic, or a simple rate reaction. These three reactions are kinetic based. This reaction is equilibrium based, and this reaction is conversion based. A conversion reaction gives you the ability to specify the extent to which the reaction will take place with respect to a base component or a base reactant. If you specify a conversion of 100%, that base reactant is utilized completely, so long as there is sufficient other reactants to carry out the reaction, or the other reactants are in excess of the base reactant. Equilibrium reactions consider temperature and pressure to determine the equilibrium position the reaction is taking place in for reversible reactions. That means that as the temperature and pressure changes, the reaction can shift more to the left or to the right, and HYSYS will determine what the equilibrium position is. For the kinetic reactors, you specify kinetic models for the reaction, and HYSYS then calculates the rate of reaction. This rate is done on a per unit volume or unit mass of catalyst, or based on the residence time in the reactor vessel. Note, kinetic reactors may not always reach equilibrium, as there may not be sufficient time for the reactions to take place to the point of equilibrium. Equilibrium reactors are utilized best when we know that the reactions are sufficiently fast that kinetics no longer play a major role. Conversion reactions are utilized when we have information from literature that suggests from experimental data a certain conversion is achievable. Note, if you specify a wrong conversion, your process will not be realistic, or may not be realistic, because your process says that the reaction would go beyond equilibrium. So we're going to add a conversion reaction to start. So click Conversion, Add Reaction, and a reaction is added. Note, although the reaction set is green, saying it's ready, there are no reactions fully specified. we must specify the reaction totally. To specify the reaction, we add the reactants. In this case, hydrogen and nitrogen, and we add the product, which is ammonia. Okay. Now, the stoichiometry for the hydrogen to nitrogen conversion or the Haber process is -3 hydrogens combined with -1, the negative sign being used to denote that these are reactants, produce +1 ammonia. Now, note that this reaction is not in balance. That means that the stoichiometry is wrong. HYSYS gives you the ability to balance a reaction where you can specify 2 of the stoichiometric coefficients and have HYSYS balance the third. If you were to do the stoichiometry by hand, you would know that N2 produces 2 molecules of ammonia. Now that your reaction is balanced, you can now specify what the conversion is. From literature, a single pass conversion through a converter, an ammonia converter, is roughly 20%. In which case, 20% of the base component nitrogen will be converted. In this case, we know that the ammonia converter is in the vapor phase, and it would have made no difference leaving it as in the overall phase. So overall phase or vapor phase would make no difference because the entire feed and contents of the reactor is in the vapor phase. However, if this was somehow a feed containing liquid and vapor, you would now be specifying that 20% of the nitrogen that is in the vapor phase will be converted. Note also, we can have a conversion based on temperature as well as some constant conversion, where C1 can be applied to T and C2 to T squared, where C1 and C2 can be positive or negative in order to achieve a fit for conversion. Now that we've set up the conversion reaction, notice that it's gone green and it's ready for use. Now we're ready to go into our simulation environment. Here we will add a feed, and in this feed we shall specify an inlet temperature of 300 degrees, a pressure of 80 atmospheres, and a molar flow of 1000 kilogram moles per hour. Our composition will have very little methane, very small amount of ammonia, even smaller amounts of those components. Sorry, we want to specify the nitrogen as 0.2 and the hydrogen as the remainder, 0.777. Right? Mole fractions equal 1. Our stream is fully defined. To access the conversion reactor, we will use the function 12 key. Go to Reactors, and we will utilize a conversion reactor. You will see a conversion reactor is added to your flow sheet. You can specify stream 1 enters it, stream 2 exits as the vapor, stream 3 exits as the liquid. A liquid stream must be specified even though a liquid may not be present. We shall leave the duty empty for now. We shall not specify a duty variable. And we will have no pressure drop in the reactor, which is unlikely. In a real process, this pressure drop would vary based on the actual degree of or the void factor or the voidage factor of the catalyst present, and as the catalyst deteriorates, this pressure drop would increase. But for our ideal reactor here, we shall leave the pressure drop as 0. Right. Unlike the Gibbs reactor, the conversion reactor needs you to specify what reactions are taking place. So note, you specify reaction set 1 that we created, and the default, there is only one reaction present, so the entire reaction set is solved. Note, it predicts the outlet temperature based on the fact that the reaction is exothermic. And as before, in the Gibbs reactor, we can look at the molar flows to get an idea of how much reaction is taking place. If you looked at the Gibbs reactor video, you would have seen there was some methane production taking place in the reactor, but this time we are not using the Gibbs free energy method to predict what reactions are taking place. We have specified what reactions are taking place. Therefore, there is absolutely no methanation taking place. And we can see that the methane entering is the same thing as the methane leaving. No CO, CO2 or water is utilized. Only the hydrogen, nitrogen and ammonia change. You are producing 90 kilogram moles of ammonia. Again, if you looked at the Gibbs reactor video, you would have seen that we could have changed the temperature of the inlet and affected the conversion. Note that had no effect for a conversion reaction. We have already specified the extent to which the reaction will take place. If you wish your reactor to not be adiabatic but to be isothermal, you must add an energy stream. This gives you a degree of freedom, and you may specify that the inlet temperature would be the same as the outlet temperature. In a previous video, I showed you how to use a set block to have this temperature automatically set by another temperature. Note, however, that though the reaction is taking place at a lower temperature, you have not changed the outlet composition, as temperature and pressure now have no effect on the predicted outlet composition. We are now going to set up an equilibrium reaction and look at the difference between the two. We return to the properties environment and we're going to add a second reaction set. We shall add it to our fluid package. And this time we will add an equilibrium reaction. Note we must configure the reaction by entering the stoichiometry. We know that we utilize 3 hydrogens, 1 nitrogen molecule, which is N2, to produce 2 ammonia molecules. System is balanced. We no longer have to specify any conversion because the extent will be predicted by the equilibrium. Note, the Gibbs free energy method will be used to predict K equilibrium, or we have the ability to enter an equilibrium relationship as a polynomial in T, or a fixed equilibrium, K equilibrium, or even as a table. Information such as this polynomial can be gotten from literature such as papers. For now, we will let Gibbs free energy calculate our equilibrium, or K equilibrium. We have the ability to specify an approach. The approach tells us the difference between the outlet temperature of the reactor and the equilibrium temperature that should have been achieved. Note that this difference is not due to energy being removed from the surroundings or added to the surroundings. This difference occurs because a catalyst may be present that does not allow the reactor to reach equilibrium. Insufficient catalyst is present to allow the reactor to reach equilibrium. Therefore, the outlet temperature does not achieve the equilibrium temperature. In the case of ammonia conversion, the reaction is exothermic. Therefore, if your reaction is not allowed to reach equilibrium, your outlet temperature is likely to be lower than equilibrium. We will return to this in a minute. So, we go to the simulation environment and we are going to add an equilibrium reactor. We shall copy the entire stream data for the feed, or for one, and we shall paste it. We have a fully defined stream, exactly equivalent to stream 1. F12 key will bring up our menu palette. We shall choose an equilibrium reactor, which we will now configure. So entering will be stream 1-2, 2-2, vapor, 3-2 liquid. Right. Three dash two. Sometimes HYSYS is a little bit buggy. Three dash two. Right. Okay. Now that we have set up the reactor, we need to specify, well, we will leave the delta P for now at 0. But we need to specify which reaction set will be utilized. The second reaction set is the one that had the equilibrium reactor. The first reaction set was the one that had the conversion reactor. If we try to use the reaction set 1, it would tell us reaction set 1 is not of the correct type because it is a conversion reaction and not usable in an equilibrium reactor. Specify set 2, and it knows that reaction 2 is applicable. It is using Gibbs free energy method to determine the K equilibrium, and we can see that it has predicted an outlet temperature of 441.7. We will add a duty stream as before to make the reactor isothermal. And specify an outlet temperature of 250 degrees. Right. Let's look at the molar flow of stream 2.2. Here we can see the ammonia production is 368.78 as opposed to 90 kilogram moles. Note also that this reactor, like the Gibbs reactor, is sensitive to changes in temperature and pressure. So that the composition will reflect the equilibrium position. In the following video, we will look at a kinetic reactor as the third type of reactor in the series.